All right, guys, sorry about making this in a two-part video, but I just want to make sure that you guys get all of the information that you possibly can, and my videos only allow me to record in 15-minute increments. All right, so based on the fact that nuclear decay occurs, okay, and it gives off different types of particles, I am able to write nuclear reactions as an equation. However, I have to keep in mind the law of conservation of mass, which means that matter, right, we know that matter makes up everything, cannot be created nor destroyed, right? So what you start with has to equal the amount of what you end with. It may change its identity, but it cannot disappear or come out of nowhere, okay? So writing nuclear reactions, we need to keep this in mind. And how we do that is that we have to make sure that my mass number and my atomic numbers on each side equal one another. Okay, so we're going to start first with my alpha decay reactions. Okay, so in this example, we have radium-226 transmutates, okay, meaning it's going to undergo alpha decay. Okay, and I write the nuclear reaction equation shown. Okay. And I'm going to be asking you to write these types of nuclear reactions soon, so keep this in mind, right? So if I look at radium-226, okay, I can write that as a nuclear notation by looking up radium on my periodic table, and I find out that my chemical symbol is Ra. All right, and when I find Ra on my periodic table, I see that it has an atomic number of 88. And I know my mass number, okay, is 226. Okay. Radium undergoes alpha decay, right? Which means that alpha decay, based on the table that you had created, can be shown as a particle of a helium isotope. Okay, so my chemical symbol is He. I have 2 protons and 4 is my mass number, okay? If I was asking you to solve for this unknown, right? This is where the law of conservation of mass comes into play, right? If I had 88 protons on this side, I know I have to have 2 on this side, right? I have to make sure that both sides have a total of 88, right? Which means that if I have 2 here, my number here has to be 86, okay? Same thing here. If I have 226 here, I know my mass number on the other side is 4, right? I know that my mass number, in order to have both sides equal 226, is going to be 222, all right? So 222, 86, and when I look on my periodic table, I see that the element with the atomic number 86, right, is radon, Rn. Okay. So based on that, what I want you guys to do in your notes is I want you to write the alpha decay reactions for these 3 atoms. You can pause your video and start writing them down, check them with me, or you can continue your video and check them all at the end. All right, so we just practiced doing alpha decay reactions. Now we're going to move on to beta decay. This gets a little bit more complicated. Okay. So I want to write the nuclear equation for a beta decay of boron 12. All right, I'm going to start the same way that I did with alpha decay, right? I know I have boron, and when I look that up on my periodic table, I know that it has the chemical symbol of B. Okay. B has an atomic number of 5, and I'm given my mass number of 12. If I undergo beta decay, I know that my beta particle looks like this, all right? I now have to keep in mind my law of conservation of mass to solve for what this would be, right? I know that on both sides, okay, my mass numbers need to equal each other. So if I have 12 on this side and 0 on this side, in order to equal each other, my mass number for my unknown would have to be 12. Okay. For my atomic numbers, I have 5 here, and I have -1 here. okay? To solve for my unknown, I have to keep in mind that what minus 1 gives me 5, right? So I know that my missing number has to be 6, right? So I got 12 and 6 now, and I look at my periodic table for my atomic number of 6, and I figure out that it is carbon. All right, so just like with alpha decay, we are going to move to beta decay, and you're going to practice these 3 reactions. You can pause your video and start working on those. All right, the last type of particle we have is gamma rays. Okay, so gamma radiation. For this example, I want to write a nuclear equation representing gamma radiation. Okay, and it's starting with unstable cobalt-60. Okay, so cobalt-60 has an atomic number of 27. Okay, it has a chemical symbol of CO. Make sure that second O is lowercase. And if it undergoes gamma radiation, right? We said that gamma rays have no mass number and no atomic number, right? Which means that this and this, right, the top number and the bottom number would be zeros, right? If a 0 is here and I know that I need to equal 60, my mass number would be a 60. If I know I have a 0 here and a 27 here and they need to equal each other, a 27 comes here, right? I look back at my periodic table and I see 27 is still cobalt. So for every gamma radiation that occurs, okay, my element does not change at all. All it does is it gives off energy, okay? Gamma radiation has no impact on a mass number or atomic number, okay? It stays the same and only gives off energy. And gamma decay can happen alongside another decay event, meaning I can have beta decay and also gamma rays. I can have alpha decay and have gamma rays, right? So it can happen alongside another type of radiation. Okay. Our last thing that I want you guys to keep in mind is other particles that may exist, because I'm going to have you guys practice writing out different types of nuclear reactions, okay? If I talk about a proton, okay, I know that a proton would have an atomic number of 1 because atomic number is 1 proton, okay? I know that proton plus neutron gives me my mass number, so I would have a 1 here. And I can write it as a P, or I can write it as hydrogen because I know hydrogen has an atomic number of 1. Okay, so I'm a hydrogen nucleus. I know neutrons, okay, we said it was a symbol of N. Neutrons have no atomic number because they're not protons, but I can have a mass number of 1 because it's protons plus neutrons, okay? We've already looked at the relative mass, right? We've said they're pretty equal with mass. We already talked about how protons are a positive charge and neutrons are neutral. And penetration power, right? Protons are pretty low. They're right up there with that alpha decay. Neutrons, however, are extremely high penetration, right? They're even stronger than gamma decay, right? So gamma rays are actually a little bit weaker than neutrons. Neutrons are the most dangerous. Okay, so based on this information, what I want you to do is I want you to fill out the worksheets that you picked up at the front of your classroom, okay, until the end of class. Make sure you get them checked and then take your Mastery Connect quiz by the end of today's class. Okay, thank you guys.